this session. So first of all, I'm actually sharing the page of the book which I uploaded in the Google Classroom. The book is by John E. Freund. It's Mathematical Statistics. And there I'm going to explain what conditional probability is. Probably some of you already know what conditional probability, but yet since it is there in the syllabus, so it is my duty officially to introduce the subject matter to you. Now, the most important part is that whenever we calculate probability, we actually should consider the sample space, as I have mentioned in my previous class with CSE section B, that sample space is the most important thing, which if not known, then probability of the event cannot be calculated. Okay. Now, also what the matter which is written over here, the conditional probability or about the sample space, it has actually been discussed. The relevance of the sample space has actually been discussed in the last class. Now, sometimes with respect to the situation and or with respect to our requirement, we sometimes squeeze the sample space. Okay, we actually try to find out the probability chance of an event with respect to a sample space which is not the original one but a modified one, which contains lesser number of items in it. Okay, so in such a situation, if such a scenario arises, then in that case we actually deal with conditional probability. We actually use conditional probability. Conditional probability are known as those probabilities where some conditions on the event are given, that a particular event has already happened. On the basis of that, the probability of the other event has to be calculated. Okay, so here is an example. First of all, they have provided a very good example, so I have decided to discuss this example with you. So first of all, I'm going to discuss this example. The question is, a consumer research organization has studied the services under warranty provided by the 50 new car dealers in a certain city, and its findings are summarized in the following table. Okay, now they have made a chart. On the left hand side of the row, they have mentioned in business 10 years or more, good service under warranty, the first column, and this is the first row heading. Second row heading is in business less than 10 years, and the second column heading is poor service under warranty. Now, the figures which are there in the table, these figures are actually the number of car dealers. Say, for example, if I consider 16 is the number of car dealers which are in business for 10 years or more, and they provide good service under warranty. Whereas 20 car dealers are there where they are in business for less than 10 years, and they provide poor service under warranty. So this is the chart we have with us. Now, the requirement is, if a person randomly selects one of these new car dealers, what is the probability that he gets one who provides good service under warranty? Okay, if a person randomly selects one of these new car dealers, what is the probability that he gets one who provides good service under warranty? Now look at this line carefully. First of all, if I add all these figures present in the table, so for example, if I add 16 with 4, 16 plus 4 is 20, 20 plus 10 is 30, 30 plus 20 is 50. So actually the total number of these figures is actually giving you the value 50, which is the total number of car dealers in the city. Now, they have considered that if you choose a car dealer randomly, then what is the probability that he gets one who provides good service under warranty? So when we talk about this, what we shall stick to this particular column. This is my column. Okay, because this is the column which represents the number of car dealers which provide good service under warranty. Some of the car dealers are in business for 10 years and more. Some of the car dealers are in business for 10 years or less. So I have to stick to this particular column. So total number of items. Now they have denoted the the denoting of events is also very important. I told in the last class that events are actually the subsets present in the Boolean algebra. So here you have to define what event you are actually dealing with. So first of all, they have assumed that capital G denote the selection of a dealer who provides good service under warranty. They have named the event as capital G, and let small n g is the cardinality of capital G. Capital G means if this is your event, what is the cardinality of this particular event? So ng denote the number of elements in capital G, because events and sets, these two items are actually similar to one another. When we discuss probability, then we call the sets as events. Okay. Now, when we get the number of the car dealers providing good service under warranty, and if we denote this by capital G, then this is my favorable number of case with respect to the classical definition of probability. And we need to have the total number of possible outcomes, which is actually the cardinality of the sample space. So here the sample space, total sample space has been denoted by capital S, and the cardinality of S, as you know, it is 50. It is given. So therefore, probability that if you select a new car dealer, what is the probability that he will provide a good service under warranty? So they have simply applied the classical definition of probability, which goes as follows. Probability of G is equal to Ng by Ns. Now, Ng is 16 plus 10, which is 26, and Ns is 50. So they have got this probability. This answers the first question. Now, first question doesn't deal with conditional probability. No condition has been imposed upon that. Okay, it is not a conditional probability. It's just a probability, just an event and just a probability which I've calculated using classical definition. Look at the next problem. Next problem is important. In the first problem, your sample space is containing the actual size, that is 50. Now, with respect to the situation given in the next line, let us see what are the changes that occur in the sample space. Okay. So they have asked, if a person randomly selects one of the dealers, who has been in business 10 years or more. Okay, fine. So they are sticking to this particular column. If a person randomly selects one of the car dealers who has been in business for 10 years or more, what is the probability that he gets one who provides good service under warranty? Now, Nihal, you want to say something? You can write in the chat box. Or I'm just a minute. Want to say something? You can unmute yourself and ask. You have raised your hand. Anything you want to say? Okay, I think it is by mistake. Now, if a person randomly selects one of the dealers who has been in business for 10 years or more, that means, you see, now the person wants to select the car dealer from this column, this particular row only. He has studied the market and he has identified the number of car dealers which are in business for 10 years or more, or 10 years or less. Now he has decided that he is not going to select the car dealer from those who are in business for 10 years or less. He wants to select them from the set of car dealers which are in business for 10 years or more. So on the basis of this condition, he wants to find the probability that what is the chance that the car dealer selected will provide a good service under warranty. In this particular case, you cannot say the total sample space is 50, because your total sample space, the size of the sample space has reduced. The size of the sample space has reduced, and now the size is 20. 16 plus 4, 20, because you are only confined in this particular row, not in the entire chart. Now, with respect to that sample space, the size of which is 20, you want a person who will give you a good warranty, good service under warranty. So that number is 16. So probability will be, I'm not going to the next page. Whatever they have written, we shall discuss it later on. But before I look into the solution, I'm doing it by my own way. So in that particular case, the probability will be good service under warranty, favorable number of cases 16, and the total number of cases will be 16 plus 4, that is 20. I think it should be the probability. So 16 by 20 is the probability. Okay. Now what has happened over here? Original size of the sample space was 50. Here the size of the sample space has reduced to 20. Okay, so now let's check what they have said. Now for the second question, we limit ourselves to the reduced sample space, which consists of the first line of the table. That means first row of the table. That is the 16 plus 4, that is 20 dealers who have been in business 10 years or more. Of these, 16 provide good service under warranty, and we get probability of what they have written. Capital T, it is denoting selection of a dealer who has been in business 10 years or more. So selection of the event and naming of the event is very important in calculating the probability. So they have defined that capital T be the event where you are deciding the dealer from the section who are in business for 10 years or more. That event, that thing is being defined by capital T. Once you select this, so this right-hand side of the bar, it has already happened. Your selection has already been made. You have already decided that I'm going to stick to that section only. What is the probability you are going to get the good service? So capital G was already defined. So probability of capital G given T, that would be 16 by 20, which is 0.80. Okay, this answers the second question as should have been expected. And probability of capital G by T is considerably higher than probability of capital G. It is quite obvious because size of the denominator has decreased in the second question. So it's quite natural, you think, what you have found with respect to the calculation. The natural part is that I am going to say, for example, I am going to select a few people, a person who can dance well. Say, for example, from the entire class of, I'm taking the girls only who can dance well. But I do not know who can dance well, who is actually taking lessons outside, professional lessons. So I am seeing all of them. I'm selecting a girl. What is the probability that she can dance well? This probability will be lesser if I know that there are a few number of girls who take professional lesson. Okay, there are 5 girls who take professional dance lessons outside. Now I'm going to select one from them. What is the probability that she can dance well? So that is, or she knows Kathak, or she knows Bharatnatyam. So when I decrease the size of the denominator, then probability definitely will increase. Okay, so in conditional, probabilities are always greater than the original probability. Okay. Now, this particular part, I'm reading it out for you. It is very important for understanding. So I'm just reading it out. Since the numerator of probability of G given, we shall read this particular thing as capital G given capital T. What does it mean? Capital G, I want to find the probability of the event capital G given that capital T has already happened. So since the numerator of probability of capital G given T is N of T intersection G, which is 16. T intersection G means T and G are happening together. Means what is T? The person is in business for 10 years or more, and he can provide good service. this is happening together. So n of t intersection g, that will be 16. In the preceding example, the number of dealers who have been in business for 10 years or more and provide good service under warranty. And the denominator nt, the number of dealers who has been in business 10 years or more only. Okay, so probability of g given t is actually number of persons present, number of car dealers in business providing in business for 10 years or more providing good service, divided by number of dealers in business for 10 years or more. But what you can do now, that mathematically you can do one trick. You can divide the denominator and numerator both by the total sample space, size of the total sample space. So they have divided n of t intersection g by ns and nt by ns. You can do it because ns and ns will cancel each other, and in that case this thing will remain as it is. Okay, now by using the notation of classical definition of probability, or you can say axiomatic approach, cardinality of t intersection g by cardinality of s, this can be written as probability of t intersection g, and cardinality of t by cardinality of s can be written as probability of capital T. So we have got a kind of thing, an expression which goes like this: probability of g given t is equal to probability of t intersection g by probability of t. Once I get this idea from the example, now I can define the conditional probability as follows. So conditional probability goes like this: if capital A and capital B are any two events, if capital A and capital B are any two events in a sample space capital S, and probability of A is not equal to 0, the conditional probability of B, given that A has already happened, is written as denoted by probability of B bar, B slash A, which is equal to probability of A intersection B by probability of A. So we have got our formula over here. We have got our formula of conditional probability. Okay. So the most interesting part and the most important part is that in conditional probability, the size of the sample space squeezes. It becomes smaller. I hope you've understood what actually they have meant to say. I shared one note on conditional probability with you 2 days ago, or maybe day before yesterday I shared. I cannot recall. There also I have explained everything, and I have done a problem on the conditional probability, so you can go through that also to understand the thing in a better way. Okay, now I'm going to stop this share, and I'm going to do some kind of board works on the conditional probability. Okay, let's see what else we can find out from this. We have to move pretty fast because examination date has been announced, and whatever you are learning, you learn it well because you do not have much time. Okay, now we have got, just a minute, we have got the definition of conditional probability. I'm writing, just a minute. Let me put it in my lab. Okay, so the definition is, if capital A and capital B be any two events, then the conditional probability of B, given that capital A has already happened, is denoted by probability of B given A and is defined as probability of B given A, which is equal to probability of B intersection A by probability of A. But you know that probability of B intersection A is same as A intersection B. So probability of B given A can also be written as this, provided probability of A is not equal to 0. Okay. And similarly, probability of A given B can also be written as probability of A intersection B by probability of B. Okay. And we can write it only when probability of B is not equal to 0. Now, from this, let us call it equation number 1. Let us call it equation number 2. So from equation 1 and 2, from equations 1 and 2, we get probability of A intersection B is equal to probability of B given A into probability of A, or probability of A intersection B can also be written as probability of A given B into probability of B. So this formula can also be written in the following way. Now interesting part is that now if I say here I have mentioned that capital A and capital B be any two events. Okay. Let us assume that capital A and capital B are independent events. Yesterday I explained independent events. What is the connection between whether there is any connection between independent events and disjoint events or not? If they are independent events, what do we mean by independent event? Probably you have learned that independent events mean happening of one event doesn't depend upon happening of the other event. Say for example, okay, I'm going to explain what independent event is practically, but first of all, let me do a bit of mathematics over here. The happening of one event doesn't depend upon the happening of the other event. So that we know as independent events. So if A and B are independent events, it is quite natural that in that case, probability of B given A, that will be simply probability of B, and probability of A given B, that will be simply probability of A. And this thing implies probability of A intersection B. If I consider this one, this will be probability of B into probability of A. They are getting multiplied simply. Or if I consider this one, this will be same because multiplication is commutative. So in place of that, I'm going to write probability of A, and this will be probability of B. So you see, yesterday I used this kind of expression in my second session, my second video. So, so if they are independent events, so we have got a new definition. This is a definition of conditional probability. From conditional probability, we have got a definition of independent events. This is another definition. Definition 1 and definition 2 of today's class. Okay, and not only this, since this particular thing is happening on the basis of the condition that capital A and capital B are independent events, so the result, the expression which I have got over here, this expression, that in case of independent events, probability of A intersection B will simply be PA into PB. I'm denoting this expression as star. So in the next page, I'm writing that star is known as multiplication theorem of probability. Multiplication theorem on probability. Or I should write of probability. Multiplication theorem of probability. So that we know as independent events. Okay. Now, what is independent event? Independent events are like practically, if you want to, if you want me to explain the nature of the independent event, it will be like this. Say, for example, I am quietly sitting at my home and I'm playing with a coin. I'm tossing a coin. Just I'm playing. I'm passing my time. I'm my leisure hours. And suppose one of my students, he is in casino playing gamblings. He is also tossing a coin. So he has some objective, and I have no objective. I'm I'm playing with the shuffling with the coin. Okay. He has some objective. He is in his domain. He is playing in the casino. He is also tossing a coin. I'm also tossing a coin. At the same time, say, he is in America at 12 in the 12 at 12 noon, and I'm doing just the same thing at 12 in the midnight. Now, we do not have any connection. He is not calling me. I'm not calling him. I do not know what he is doing. He doesn't know what I'm doing. But we're doing the same thing. So whatever result we are getting on the basis of our respective coin tosses, these results will be totally independent of one another. Totally. So probability of A intersection B means what is the probability that the student in the casino and Sobik sir in his home are getting head together. Both of them are getting this result. What is the probability of that? So this is given the multiplication theorem of probability. Now, suppose I have some sort of connection with him, and he is actually pre-deciding his outcome on the basis of mine. Okay, suppose we are connected to one another. I'm also playing the gamble, distant by being distant from the space, from the casino, and he is in the casino, and the settlement is like this. If I toss a coin, if I get head, I have to tell him that yes, I have got head, and if he gets head also in the casino, then he can win. Otherwise, he is not. But he is totally dependent upon me because I can lie also. I may not want him to earn anything from the game. Maybe I have some sort of setting with the casino people, okay, who are watching him. So in this type of scenario, our situations are not independent of one another. Okay, so that is what we know as independent events. If the happening of one event doesn't depend upon the happening of the other. Okay, now suppose it is raining here. Right now, in my place in Assam, it is raining, suppose. In Kolkata, it is quite, the weather is quite windy and the sky is cloudy. But if I ask that in Assam, there is a heavy rain, what is the probability that on the basis of this particular fact, Kolkata will have some rain in the evening? Now, you never know whether the cloud in Kolkata or the wind which is blowing, then meteorological people know, but you do not know whether it is because of the rough weather in Assam or not. Okay, so you do not know this. In probability, what happens? Until we know something, we cannot say it, cannot give results deterministically. So if you ask meteorological department that what is today's of Kolkata, is it dependent upon the rough weather of Assam? And they are saying no, it's not like that, or yes, it's like that. They are studying it, but you are not studying. But if you are just guessing, then it is kind of probability. What is the probability that this weather in Kolkata, this gloomy weather in Kolkata is because of the rough weather in Assam? Okay, so therefore, in this scenarios, this particular in this scenario, we actually define the conditional probability. Okay, now conditional probabilities, since time is running out, I am going to I was going to do a little bit of some more calculations, but I think that if I start those calculations, I will not be getting time to complete it. So I have decided to do the calculations in the next session. So I'm stopping this share, and let's get back to the note which I was sharing. Now we were in this part, so we defined conditional probability like this. Now look at this problem number 16. The problem number 16 is saying, just a minute. The problem number 16 is saying, with reference to the example 15, what is the probability? What is the probability that one of the dealers who has been in business less than 10 years will provide good service under warranty? Now, in this particular case, what they are getting, they are, see, T prime. T prime is what? T prime is the complementary event of capital T. The T prime is the number of dealers who are in business for less than 10 years or more. They are not defining any extra, they are not using any extra notation to define it, because a person can be in business for 10 years or more, or a person can be in business for 10 years or less. So one is complement to another. So that's why they have not introduced any extra notation, capital extra alphabets to denote this. So since being in business for 10 years or more and being in business for 10 years or less, they are complementary to one another. So they have denoted T complement to denote this event, that they are in business for 10 years or less. And they are providing good service under warranty. So from the chart, they are calculating this probability to be 10 by 50. Okay, so look at this chart. Just a minute. Let us look at this chart. Just a minute. Where is it? So what was this is the chart which I was sharing with you. Now, what is the probability that the person is in business for less than 10 years, providing good service under warranty? They are actually, this probability is given by 10 by 50. Okay, and probability that they are in business for less than or 10 years, this is given as, this can be calculated as, look at, if you have the chart in front of you, just look at this to make sure that what is happening is 10 plus 20 by 50. Okay, so we get 0.60, and substituting these two probabilities in here, probability of providing good service under warranty, given that he is in business for less than 10 years, it is given by the definition, probability of T complement intersection G by probability of T complement. You have calculated both of these items from the chart, and from there you have got the probability as 1/3. Okay, so that is how we calculate the conditional probability. Let's meet in the second session, and I'm going to discuss more on conditional probability. I'm stopping the sharing right now. Okay.